Welcome to the continuation of the plastic analysis. We already have gone through 2 lectures in plastic analysis. Let us do a quick recapitulation before we go to new topics. So we begin with the working stress approach and the flaws associated with it, as well as the limit state approach. So typically, if we are using limit state approach, we assume that when the section, and that may happen only at 1 or 2 points within the entire length of the structure, that when the yield moment is reached, that is when the extreme fibers they reach the yield stress, we deem the entire structure to have reached failure. So that is the yield moment. However, the structure or the component has not yet collapsed. It can undergo further increase in the moment, because when the yield point is reached, the stress versus strain plot tells us that the point can extend further, because there are regions below the extreme fiber which have not yet reached the yield stress. So their capacity can be utilized further. So typically this is the limitation of the working stress approach. So if we use the limit state approach of design, we are much better. But then in the limit state approach of design also, we have some flaws. So the flaw is that although we are doing the design of the section very rigorously, taking into account the nonlinear behavior, but we are relying on linearly elastic analysis to obtain the ultimate moments. Basically, we do linearly elastic analysis, and whatever are the moments, we multiply them by a load factor, and we assume that these are the moments corresponding to the ultimate state. So this introduces some kind of contradiction, in the sense that we are doing very rigorous design, but for analysis we are lagging behind. So plastic analysis, it fills this gap. Plastic analysis takes into account the actual behavior of the structure beyond the yield point. So let's see what were the assumptions we had considered. We assume that Hooke's law of elasticity is valid till the yield point, and then the yield stress, Young's modulus, as well as the stress strain curve, they are same for both compression and tension. Then we assume that strain hardening region is ignored. So we have idealized the stress strain curve to purely elastoplastic. After this, we also assume that the section has at least one plane of symmetry. So we are not considering section which does not have any line of symmetry. So we had also gone through step-by-step behavior of the section till final collapse of the structure, and for that purpose we considered deliberately a monosymmetric section with different shapes and different section moduli with respect to tension and compression. For example, here we took a section which typically has a more area contributing towards the tension, so it's stronger in tension and weaker in compression. So the stress diagram is something like this, because the neutral axis is downward. So naturally here the top stress, which is compressive, is much higher as compared to the bottom stress, which is tensile. So for this case, we saw the entire sequence of plastic hinge formation as the section went from point number 0 to 1 to 2, 3, 4 and 5. So when it reached point number 2, that implied that on the compression phase we have reached the yield stress point, but on the tension side we have not yet reached. And then when the tension side reaches the yield stress at point number 3, the compression side, it moves beyond the yield point. And finally at point number 5 we have the final plastic section. So we can just brush through these sequences. Like here we have point number 1. So here basically the neutral axis is the elastic neutral axis, and is given by this expression that we have to take first moment of the area about a designated coordinate origin and divided by the total area. That gives us the location of the neutral axis. Then when we increase the loads to point 2 such that we are reaching the yield stress at the top and we have not yet reached the yield stress at the bottom, in that particular case the stress and the strain diagrams, they remain linear, but at the top a limit has been reached that after this there won't be any increase in the stress further, as we'll see in the next stage. So for this condition we can find out the curvature as the slope of the strain diagram. So just we have to add the top and the bottom strains and divide by the depth of the section to obtain the curvature. And when we reach point number 3, and in that particular condition what happens is that both top and bottom points, they have either reached or they have gone beyond the yield stress point. So in that particular case, in the case of the compression side, the strain has now exceeded the yield strain, so that's why the stress will now exceed the yield stress. So we'll have something like this. And if we go further and we reach point number 4, in that particular situation we have both the top and the bottom strains, they exceed the yield strain, as a result of which the stress diagrams would be something like this on both the sides. So we have an elastic core, and then at the two edges, near the two edges, we have the plastic region. So it's now a combination of the elastic and plastic regions. So the elastic region is called as the elastic core, and this provides us a measure of the curvature. And finally, when we reach point number 5, where both the top and the bottom portions, they have reached their full potential in terms of resisting the moment, both the stress diagrams at the top and the bottom, they have reached their full capacity. In that case we obtain the plastic neutral axis. So this plastic neutral axis is again given by the condition that the tension and the compression forces, they balance each other, and basically we find that this is defined by a location which divides the area into two equal parts. And for this particular case we obtain the plastic moment capacity given by the yield stress multiplied by the plastic section modulus. And what is plastic section modulus? It's basically each of the two areas, which is just half of the total area, multiplied by the lever arm of the compression and the tension forces. So all we have to do is find out the center of gravity of the two areas and multiply half of the area with this distance. So we also defined shear factor, which is equal to the ratio of the plastic to the yield moment capacity, or ratio of the plastic to the elastic section modulus. Now let's go further and obtain moment curvature relationship for a particular shape. And here for simplicity we have chosen a rectangular section so that we can just understand the nature of the curve. And here we have deliberately considered this section so that it's bisymmetric. So that means both the top and the bottom edges, they are reaching the yield condition simultaneously. So here now point number 2, it denotes reaching the yield stress condition both at the top and the bottom. So going further, so at point number 1 we can obtain now a simplified expression for the curvature, because both the top and the bottom strains are equal, so we take advantage of that. So it's given by 2 times the strain divided by the overall depth, and this can also be expressed in terms of stress by taking advantage of the Hooke's law. Further, if we reach point number 2, then we reach the yield moment capacity of the section, and if we are crossing point number 2 and reaching point number 3, in that particular situation we'll have elastoplastic section, that is, we have plastic region near the boundaries and an elastic core where we have the strains equal to the yield strains, and the stresses, they are such that above this they are not crossing the yield stress. So we have the elastic core DE, and this defines the curvature. So here for curvature we are making use of the depth of the core instead of the total depth as in the previous condition, that is at point number 1 and 2. So going further, so what happens is that now the plastic or the end regions, they undergo strain without increase in the stress, and any moment which is beyond the yield moment, that will be resisted by shrinking of the elastic core. So it will shrink, and a limit will come when the two plastic regions at the top and bottom, they meet, and that happens at point number 5. So then we have the fully plastic section, and the curvature is becoming infinity because the core, it reduces to 0 depth. So now if we want to derive a moment curvature relationship, we can do that. So we consider, let's say, point number 2, which is the limit when the top and the bottom extreme fibers, they reach the yield strain and the yield stress. So for that particular case, for the linear portion of the stress versus strain curve, we can obtain a relationship between the moment and curvature very easily, because we have already defined the value of the curvature. So making use of the yield condition, so the curvature at the yield point is basically given by this expression, and now making use of the relationship between yield stress and the yield moment, we can derive this relation. And when the moment is less than the yield moment, the curvature is reduced in a proportional manner. So it's a linear curve. So this portion is very easy to mathematically describe. Now what happens after point number 5? After point number 5, basically the curve is a straight line because curvature becomes infinite. Now the only portion left is in between points 2 and 5. So we can intuitively draw a curve, but what we want is, we want an exact expression for this region. So for this purpose, we do a very simple derivation for this rectangular section. So going further, now we have to convert this relationship into curvature. So that's very easy now, because right now it's in the terms of the depth of the core, elastic core, with respect to the overall depth. When we have crossed point number 2, the curvature would be given by this expression where we have the depth of the core, and when we are at point number 2, we have the yield curvature, and this is given by this relationship where we have the overall depth. So ratio of these, so now we can make use of this expression and substitute the ratio of dE to D by phi y by phi. So with this we obtain this kind of relationship. So this is essentially an expression for the moment in terms of the curvature. Now we can plot it, and to test it, what we do, we write it the other way. So we have written in such a way that the moment comes on the right hand side and curvature on the left hand side. So what we do for the rectangular section, we know that the expression for the yield moment is this and for the plastic moment is this. So we know their ratio is 3/2. So if we input this value under the condition that we have reached the plastic moment, then the curvature will come out to be infinite, and this shows that our equation is correct. Now it's your homework to obtain an expression for the curvature at the onset of the plastic stage, that is when m is equal to mp. Now how would you find it? So I am giving you a clue that this equation has a point of singularity at m equal to mp. So all you have to do it is just use a value slightly less than that. Say you can use 90% of the plastic moment, and by doing so you would be able to get reasonable value of the curvature at the onset of the plastic stage, that is phi p. You have to obtain expression for curvature at this point. Now if we take this further to the moment deflection relationship, the moment deflection relationship can also be predicted that it will be linear till point number 2, because we have the linear stress strain relationship, and after point number 5 we know that it will be a straight line, because at point number 5 we reach the condition of the collapse, that is the structure is reduced to a mechanism, and when the structure is reduced to a mechanism the deflection will be infinite. And in between the two, what we find, we have here point number 2 the state of stress is like this, point number 5 we have the state of stress like this. So in between the curve will be like this. So just like we have derived the expression for moment curvature, we can similarly derive an expression for moment deflection also. Now let's see how the plastification happens. It does not happen at a single point, but basically it encompasses a small region. So let's say for simplicity, consider a simply supported beam under the action of a point load acting at the midpoint. So for this case it has triangular bending moment diagram. So it's a very simple structure, and here at the midpoint the bending moment is PL/4, and this is the governing moment, because this is the maximum bending moment anywhere in the beam. So let's increase this load in a gradual fashion, and we can just understand how the structure undergoes plastification. So if we are increasing the load gradually, and if we are increasing it to the yield load, so that we have the moment reaching here the yield moment, so what happens is that at the two extreme fibers we have reached the yield stress condition. And if we now increase the load further, so what will happen, that we are considering the condition that we have crossed the yield moment at the midpoint, but we have not yet reached the plastic moment. So the section is still resisting a moment much below the plastic moment. So now if we see the bending moment diagram, we find that this particular region in the middle, which has a length LP, so here all points they have exceeded the yield moment. So that means some kind of plastification would have initiated in these points. So basically this region is under plastification, and if we try to draw the region of plastic development along the length of the beam, it would be something like this. So all the points which are lying within the red zone, they are undergoing stresses larger than the yield stress. And if we increase the moment further, what will happen is that the two regions, they will tend to come closer to each other. So let's do that. So now if we want to find out what is this length, we can very easily find, because at the end of this region we have a moment equal to my. So all we have to do is that instantaneous load multiplied by this distance that gives us moment, and this moment must be equal to my. So using this equation we can find out the length of this plastic region. Now if you increase the moment further and make it equal to mp, then what will happen is that this plastic zone, it increases, and it increases to its limiting value. This particular load can be obtained very easily by the general expression of the bending moment at this point. All we have to do is substitute the moment by mp, that is the plastic moment, and this will give us the value of the ultimate load. And now here the two plastic regions, they are just meeting at one point. So at the midpoint of the section we have fully plastic section, but it's not there as we go away from the midpoint. So if we go away from the midpoint, we come across the region where there is moment equal to just yield moment, and further away from these points on both these sides we have the sections still in the linearly elastic range. So if you want to find out the length of this particular portion, which is the limiting length, then we can use the previous expression, and what we have to do is we know the value of the ultimate load now. So if we substitute this, then we get this equation. So for a rectangular section, because the shape factor is 3/2, so we get this length to be 1/3. So that means when the plastic hinge is formed, basically the middle 1/3 region of the beam is under some kind of plastification. So plastic hinge, theoretically it appears to be a single point, but it is basically a region. The adjoining regions, they also are part of it, though they don't fully contribute. So it happens such that at one particular point we have fully plastic section, but it's not the case in the regions to the left and to the right. So they try to resist the plastification process because they still have the moment capacity. So we'll see how a plastic hinge actually looks like. Now it's your homework. You try to find out the shape of this curve along the length of the beam. Is it linear or does it follow some other non-linear equation? Now we have already derived the moment curvature relationships. Now it must be noted that even if the section reaches the fully plastic curvature, it does not fail or rupture. This is because the material is assumed to be highly ductile. Typically, the rupture happens at curvatures typically which are at least 5 to 10 times the plastic curvature. So what happens is that theoretically, if we use the moment curvature relationship that we have derived, it appears that the curvature variation along the length of the beam would be like this. But the actual variation is something like this. Now why this happens? Because the plastification, in the sense that the top and the bottom regions, they are converging, that happens at a single section only. The regions to the left side and to the right side of it, they still have capacity because they have not yet reached the yield stress across their entire depth, so they tend to resist. So the actual curvature distribution along the length of the beam is something like this, and it's different from the theoretical one. So theoretically, curvature is infinity at this particular point, the midpoint, but this does not happen because of the resistance from the adjoining portions. Now this phenomena is called as unrestricted plastic flow. So basically it culminates in the formation of the plastic hinge and our total mechanism. Now here we are just showing you some of the pictures of plastic hinge. So this is plastic hinge formation. So what we are showing here is the top view, and here we have the side view. So you can see that the plastic hinge is not just one point, but there is a region. And this is the complete view of the frame. So here the end conditions, they are not simply supported. So here we have a bit short length. And this is a plastic hinge formation in a real structure which underwent failure under wind. So what we can see here, that it is the formation of the plastic hinge, but at the same time there is local buckling also in the web. And here we are showing you a test involving a bamboo frame. So it's made up of fiber reinforced bamboo composite sections, a different kind of system involving bamboo. So here in this particular frame, which is a portal frame, the loads are applied both horizontally and vertically in a simultaneous manner, and we can see the formation of the plastic hinge in the beam. So we are just zooming this region out, and you will be able to see the plastic hinge from a closer sense. So as against the theoretical perception that it's a point, basically it's not a single point, but it's basically a region. And basically the region is such that we can see very large deformation within all points of this particular region. So thank you very much. We'll continue after this in the next lecture.